Chapter 2, Atoms and Elements. This quote is from John Dalton. These observations have tacitly led to the conclusion, which seems universally adopted, that all bodies of sensible magnitude are constituted of a vast number of extremely small particles, or atoms of matter. People kind of talked a little different back in the 17 and 1800s. Let's think about this. Say, you're doing your homework and the tip of your pencil breaks off, a little piece of graphite. If you take that piece of graphite and you cut it in half, and you take one of those pieces and you cut it in half, and you keep doing that, how far can you go? Just imagine that you had a knife that was small enough to just keep going. Could you keep doing that forever? Or would you come to some smallest particle? This was a big question. So, turns out, eventually you'll get down to a piece that's 2 carbon atoms, and you could cut that in half and have individual carbon atoms, but you can't cut a carbon atom in half. The word atom comes from the Greek atomos, meaning indivisible. So you can't divide the carbon atom into smaller things and still have carbon. The atoms are the building blocks of all of matter. I think of them as being like round Legos, right? So you can take the structure apart into those individual bricks, and you can combine those bricks in different ways to make different things. But you can't break, I need a shorter piece. I'll just break this one in half. You can't do that, right? So that's what atoms are like. In 1827, Robert Brown was looking at particles that came from pollen grains, and these were suspended in water.
The best thing is that I never really have to be the same, but I'm always
good for
me.
you. So the big things there are the grains of pollen, and then you've got these little tiny things, and they're wiggling. What's making them move? What are they? So this was an observation that led to a hypothesis and a law. What was causing this motion? Bless you. So Brown initially thought those particles might be alive. They sure look alive, don't they? But he finally concluded that the source of the motion was not the particles themselves, but the stuff around the particles. The water. So 1905, Albert Einstein, you've heard of him, developed a theory that explained Brownian motion as a molecular bombardment of the water molecules. So that video showed us what can be seen through a microscope, those little particles. So those particles are large enough to see through a good microscope, but water molecules are too small to be seen with any visual microscope. So what we can't see is the water molecules hitting those little particles. So they're like a beach ball thrown out into a crowd. So let's say we've got glow-in-the-dark beach balls, or maybe a fancy one with lights in it or stuff, and they turn off all the lights in the stadium and people are hitting the ball. What would you observe from a distance? You would just see this beach ball moving around. You could see the people hitting it, right? You're like, how is it doing that, right? So it's the water molecules. Remember, even in a solid, particles are not completely still. They're wiggling, like you guys are, right? And then in a liquid, they're actually moving around relative to each other. And when they bump into those particles, they cause them to wiggle. Okay? So this theory and observation inferred the presence of atoms, the existence of atoms. And then a guy named Jean Perrin conducted some experimental measurements that confirmed Einstein's theory, and then there was no more doubt about the particulate nature of matter. So you may notice in this chapter especially, there's a lot of dates and names. I am not testing you on chemical history, the history of chemistry. That's not part of the curriculum. But I want to use their names and mention the dates because it gives us some context, right? So don't stress about that. So back in the 1980s, a couple of guys at IBM were doing some work that led to the development of what's known as a scanning tunneling microscope, or STM. And the idea here is that you have this probe that's controlled by a computer, and it can scan, it can raster back and forth across the surface. At the tip is a very, very pointy needle. At the end is just one atom. And if you apply an electric voltage between this probe and the surface, you can get a current to flow. The current will be dependent on the distance between those two objects. So what the computer does is it measures that current, and as it's scanning the object, it will raise and lower the probe to keep the current the same. And so it's raising it, it comes to a bump of an atom and it comes up and down. And it can do this precisely enough to give us some kind of fuzzy images of atoms. So this is the kind of picture you get using STM. So here we have, these are the Japanese kanji characters for atom. So we have the iron atoms are these purplish red bumps, and then the background is copper. So copper surface, and they use this technique to move some iron atoms to spell out kanji characters. Okay. Scientists do some pretty weird things when they have a little time. Oh yeah. It's like there's a video. It's right here. How do they
So
make
what we
those?
do to move atoms is a variation of what we do to see the atoms in the first place. So we can't use light to see them. So we're not looking through a microscope like the conventional microscope we're used to. We need something that can see much smaller things than that. So what we do is take a sharp metal needle and bring it close to the atoms. And in a sense, we're feeling the shape of the atoms. So if you imagine that we have a surface that we're putting an atom on, we put it on the surface and so it holds still. What we do is take this metal needle close to the atom and sense its presence by measuring an electric current that flows. And as the tip of this needle approaches the atom, it sees more electric current, and we draw it up and over the atom to keep that current constant. So in a sense, we're feeling the shape of this atom. Then in order to move atoms, we observe that we have a sharp metal needle near it. We can bump into it by accident. What we can do is, instead of doing it by accident, do it under control. If this is our atom on a surface, we can move the tip close and we start to form a chemical bond between the tip and the atom. That chemical bond forms between most atoms. They like to bond to each other in most cases. So we start to form a bond such that the atom follows the tip around on the surface. We can drag it to a new spot. When we withdraw the tip, it holds still because the surface is holding it in place. And we can take an image and see where we've placed this atom. So that process, repeated over and over, is how we've built most of the structures in our lab. That's our bread and butter basic technique for moving atoms around.
So that's how they were able to move these iron atoms around and spell this out. Okay, so, doing that is like cool and everything, but what good is this? Well, you can use this to make really, really tiny circuit boards, right? Instead of having to paint on some metal to form connections, you can actually just move atoms and make really, really thin wires on a surface. So that's one of the things that IBM does. And so there's this picture, and then they also made a movie. So this is the world's smallest movie. I just think it's fun. This is basically very high-tech stop-motion animation. Move an atom, get the picture. Move an atom, get the picture, put them together. Isn't that cool? So, essentially, those atoms are like the ultimate smallest pixel, right? You can't get any smaller than that. Anybody have any questions about that? I have a question. What was I doing? Okay. So, just trying to help you get an idea for how small atoms are. So the Library of Congress has about 35 million books. If you lined them all up, stacked up right, they would take up 840 miles of shelves, right? So you take all those books and think about all the letters in all of those books. If you were to write those using letters the size of those kanji characters, like maybe 10, 15 atoms tall, you could fit all the letters in an area of 5 square millimeters. That's half a centimeter on a side. I'm sorry, it's not even half a centimeter. No, it is. Never mind. It's half a centimeter. Isn't that amazing? I mean, just so small. Atoms are the key to understanding the rest of matter. So the atom is the smallest identifiable unit of an element. There are 91 naturally occurring elements, and there's over 20 synthetic elements. Those are made in labs, and they're not naturally occurring because they are so unstable that they just, you can make them and then they just fall apart, sometimes even before you can make enough to get a mass or even tell what color it is.